Alright, we're going to go ahead and get started with section 2 of our thermochemistry unit. And in this section, we're going to focus on the different types of systems that we'll come across and we'll deal with in chemistry. Understanding the term enthalpy and what it means in terms of the energy. Describe how energy transfer is facilitated through calorimetry. This is one specific type of way to measure the change in energy, as well as to describe how to calculate energy changes based on the equations. Now, as we're going through this, I want you to take the time to make sure you rate yourself on our scale, again being 1 at the very bottom, I don't understand what's going on, all the way up to 4, where I understand it and I can move on and apply this in different ways and forms. The first type of system that we're going to deal with is an open system. Now, an open system is what we deal with on a regular basis. Given by the example here, we have the pot on the stove with boiling water. We're able to have water vapor leaving, but also we can feel the heat being released or gained through the system. The diagram here on the side sort of gives us a better picture. The second system would be a closed system. In this situation, we'll have energy transferred, but we'll have what's called matter being conserved. What do we mean by conserved? Conserved means it can't go anywhere. It's stuck in that situation. And this may be similar to us doing something as simple as putting a lid on the pot. It's still boiling, but now we have a lid on the pot. We're able to feel the heat off of the pot and different things, but we're not able to lose any water vapor. It's trapped inside. And the least common but most effective system that we'll deal with is an isolated system. In this case, both energy and matter are conserved. What do I mean? There's no way for energy to get in or to leave. So we cross that out. It's not going to even be a factor for us to deal with in this case. Now, sorry. Oops, let me go back one slide. Now, an isolated system is what we're going to deal with when it comes to calorimetry. A calorimeter is a mechanism or a device that's used so that we can use an isolated system to see exactly how much energy is transferred in or out. As you see, majority of the space is filled with water here. And inside you have a little chamber that actually has the reaction where it's going to take place. When this reaction takes place, though, the energy has nowhere to go. And so it's either transferred into the water or it's transferred from the water into the system. This gives us a clearer view of the actual energy transfer without having to worry about the competing reactions or anything happening along the side. So we can use the temperature given here as our main means of understanding what's going on. Now, what is the difference between heat and temperature? We started this discussion before, and we just want to jot down a few points. Again, you're filling out the information in your guided notes as we continue going through this. Now, the main thing with heat, is heat is just the amount of energy within a system. So as a reaction goes on, or even as these different substances are just sitting around, the particles are not sitting still. They're moving in some way, shape, or form. When we notice that in a solid, many times they're moving very slowly or vibrating back and forth. Liquid, a little bit more information, a little bit more movement as they bump around into each other, move around each other. And gas, of course, we talked about being all over the place, moving at high energy. When we look at the overall idea, high heat means that we're going to have a lot of energy. Low heat, of course, low energy. Now, how do we then measure this information? We usually use a thing called a thermometer to measure the temperature, which is just a way for us to be able to have an idea of the average kinetic energy within these molecules. How fast are they moving? The faster they move, the higher the temperature will be. This is going to be our gauge as we continue going through this unit. Sorry. Now, enthalpy. What is enthalpy? Enthalpy is just the energy flow of a system at a constant pressure. So what happens to the energy when it's under a constant pressure. We'll learn later on that if you change the pressure many times, you also have an effect on the energy that is involved in that system. So we want to look at what happens if I keep it at this constant pressure, at the same pressure. How does the energy change? The next two things we have here are a couple of examples of different ways that you'll see this information portrayed. The first will be a thermochemical equation. And this is just going to be a chemical reaction that includes the energy change, as a part of the equation. So you see right here that you have your 65.2 kilojoules as a reactant, as a product in the equation. Because of the fact that it's a product in the equation, this lets us know that this reaction will also be exothermic. It's going to release this much energy. Whereas if it was on the other side, it will be a reactant, meaning it will be an endothermic reaction. We'll continue to talk about these as we go. Another way that you may see this written is as the heats of reaction. Now, the heats of reaction just show the reaction as it is, but you notice that on the outside it has this delta H equals negative 65.2 kilojoules. And we talked about this before when we see this negative sign out front. This is our clue that it's a exothermic reaction, that heat or energy was released. Just like if we see a positive delta H value, that lets us know that energy was absorbed into the system. Now, we take this a little bit further as we continue to look at this, because when we look at the state changes or the phase changes, as they'll be called, we want to know what happens, or how do we basically interpret this information. Now, first thing that we run to is heat of fusion, which is energy absorbed when 1 mole of a substance or of a solid melts to a liquid. Heat of fusion is letting us know that we're changing directions, but we're changing phases, and we're going to a liquid form. So how much energy do I have to put in? And of course, many of these values are calculated for you, so you may not have to go through and look at these overall. The next thing that we'll deal with is heat of solidification, which is energy released when 1 mole of a substance solidifies from a liquid. If we're using water as our example here, and we see the direction of what's happening, this is where knowing those states that we talked about before becomes important, because depending on the direction that we're going, we may have a positive or a negative value. So the first is given to us as our heat of fusion for water is 6.01 kilojoules per mole. Each mole would take 6.01 kilojoules in order to go from a solid to a liquid. Whereas if we're going back the other way, it takes the same amount of energy, but now instead of gaining this energy, it's going to lose that amount of energy. So you want to notice that it's just opposite, same value, but the charge is different. The next state that we'll look at is the heat of vaporization versus the heat of condensation. Heat of vaporization, similar concept as we talked about before, the amount of energy that's needed to vaporize 1 mole of a liquid substance or turn it into a gas, whereas the heat of condensation is the amount of energy released when 1 mole of a vapor condenses to a liquid state. Again, still same values, 40.7 kilojoules per mole, but when we condense, we're again releasing energy into the system, into the surroundings, whereas in the vaporization, we have to absorb that energy. So with each of these, again, there's a table that you can always go back to, so don't be afraid or think you have to memorize a whole lot of information. Now, the way that we track these things is we have what's called a heating curve and a cooling curve. Paying attention to our diagram in the top left-hand corner, you notice that we may be adding heat to go from a solid trying to move towards a liquid. But it doesn't automatically just keep going up. Most people would think that the trend would continue this way. But we have this little section right here and right here. And it's letting us know that it's still in this same state, but there has to be energy given so that all of the molecules can actually get to that next level. So when we have the state change or the phase changes, we have this little section, this is our delta H of fusion and our delta H of vaporization, that are going to help us to go between those stages. And you notice that each of these is an increase in energy being added. Whereas on the other side, we have our cooling curve. As we continue to go down from a liquid moving towards a solid, we again reach a point where we sort of plateau, or where we flatten out for a moment. When we flatten out, that lets us know this is the melting point. This is the point where everything sort of freezes up, or as we normally would call it, freeze. Don't worry, we'll do a little bit more with this in just a few slides, so no fear. Now, reaction enthalpy overall is going to tell us how did it change for the overall reaction. And this is where we come to standard heats of formation, which is this nice little symbol given here to the top left of your screen. Now, this is the change in enthalpy formation of 1 mole of a substance. So, there's energy formed or stored in the bonds of our reactants and in our products, and we want to see what is the difference between those two. Now, when we deal with diatomics and elements, they usually will have a standard heat of formation of 0 kilojoules per mole. Why? They're already in their lowest energy form. They're not going to change too much. But then once we add them to something else, that's when we'll run into another system. A formula that will be very important and help us to understand what the actual change is will be our delta H, which again, H stood for our enthalpy, equals the change, the standard heat of formation of our products minus the standard heat of formation of our reactants. Reactants minus products, again, sort of final minus initial, will help us to be able to see this is what we have in the end. Sometimes this value will be negative, sometimes it will be positive. Again, if it's positive, it will be endothermic, energy absorbed, and if it's exothermic, it'll have a negative value. This concludes our section 2 of this unit. Go ahead and rewind if you have any questions or anything like that, or write down any questions for me in class, and we'll be able to continue this a little bit later. Have a great evening, and see you in class.